Okay, Daniel. So today I am going to solve 3 exercises and the remaining I will do next Wednesday. So let's start with this one. Here we have a function g from z plus into, sorry, this is not z plus, this is the set of integers z by g of n equal to minus 1 to the power n times n. We have to prove that g is injective but not surjective. Let's first show that g is injective. There are two ways of showing that a function is injective, equivalent actually, but there are two ways. Say you have a function f from a into b, and you take any two elements in a. To prove that f is injective, either you show that this implication is true or you show its contrapositive. It's up to you to decide which one you want to use. They are logically equivalent. They are either both true or both false. So for this one, I am going to choose this. In words, I will show that for any two distinct inputs, the outputs are also distinct. Accordingly, let me choose two distinct inputs. Let n1 and n2 be two positive integers such that n1 is not equal to n2. Now note that being a positive integer, n1 for example is either even or odd, and the same thing can also be said about n2. And accordingly, since n1 and n2 are independent choices, we will have 4 cases depending on whether each one is even or odd. If n1 is odd and n2 is even, you can guess why I am stressing on the parity of these numbers, that is whether they are even or odd, because we have this power of minus 1. That's why. So if n1 is odd, then g of n1 by definition is this. Oddness of n1 will make this power of minus 1 itself, and that way we will get minus n1. But n1 is positive, so minus n1 is negative. However, because n2 is positive, this is less than n2. But n2 can be written like this also. Because n2 is even, this power is plus 1. And this is g of n2. So we see that for distinct inputs n1 and n2, in this specific case, g of n1 and g of n2 actually are also distinct. It turns out that g of n1 is less than g of n2, but that's not the point. The point is that they are different. That is, g of n1 is different from g of n2. That's what matters here. Similarly, if n1 is even and n2 is odd, then also they are different. I mean their G images are different. So that leaves us with two more cases. In one of them, both are odd and in the other, both are even. Let's consider the odd first. Next, let n1 and n2 be both odd. Then, distinctness of n1 and n2 implies that their negatives are also distinct, minus n1 and minus n2. But minus n1 is G of n1 because n1 is odd. And this is different from minus n2, which is also G of n2 because n2 is also odd. So in this third case also, the outputs are different. And finally, let n1 and n2 be both even, and this is even easier. Then their evenness will give us this calculation. This is not equal to n2. So in all the possible cases, we have shown that distinct inputs implies distinct outputs. So G is injective. Next, we also have to show that G is not surjective. That means not every integer is going to appear as an output. But which integer fails to appear as an output? We need some kind of guess for that. And that's why let's just see some G values of positive integers. This is not a part of the solution. It's a rough work. We do this kind of things when we get stuck and we want some help. So what is our G? What's the definition of G? We multiply the input n by minus 1 to the power n, and that's why the output is simply the input if the input is even. But if the input is odd, then the output is the negative of the input. That means these are the outputs: minus 1, 2, minus 3, 4, minus 5, 6, minus 7, 8, and so on. So among these outputs, you can see that there are not every integer is appearing. For instance, the outputs are negative odd integers or positive and positive even integers. So positive odd integers, for example, are not appearing, and among them, for example, 1 is not appearing in particular. So that is the guess, and now we can show that 1 is really not an output. I mean, it's only a guess, okay, because the function has infinitely many outputs, infinitely many inputs. So simply by looking at some finitely many values, you cannot be sure, and that's why we need to continue. So now let us try to rigorously show that 1 cannot be an output. But how? By forcefully supposing that it's an output and then arriving at some kind of contradiction. Suppose that g of n is equal to 1 for some positive integer n, then minus 1 to the power n times n is equal to 1. So from this equation what we see is that n divides 1. As an integer n divides 1 because this left hand side is an integer multiple of n, that is why. So n divides 1. But we know from elementary number theory that only two integers divide 1, minus 1 and 1. Among them, n cannot be minus 1 because n is already positive. Thus, n has to be equal to 1. That, however, is not possible. Let's see what goes wrong if n is 1. But then if n is 1, that this n vanishes because it is 1. But this power of minus 1 is minus 1. So we get minus 1. And yet it is also simultaneously equal to 1. Okay, so this is our absurdity. So no such n exists. Hence, G is not surjective. Whenever we see a solution where we went through some kind of argument, it is not a calculation solution, it involves some argument, logical argument. Sometimes we don't understand why someone does this step or that step. Behind such, I should not say misunderstanding, but behind such confusions lie this type of rough work, which of course are not shown as parts of the solution. This rough work can be done in the middle of the solution, I mean while doing the solution, or before starting the solution to get a rough idea of how you should even begin, or towards the end of the solution also. The unfortunate thing is that these things cannot be shown. Everything cannot be shown. I mean, a solution is just the final product. You don't show how you got that. And that's what makes sometimes these things very confusing. But you can, of course, guess more or less what to do when you get stuck. It's not that every time you will get an idea of what to do next. But in most of the cases, if you go through simple values like this or you draw a simple diagram, that is enough in most of the cases. Next is exercise 33, and this is the one you specifically asked me to solve. Define a function, this time from the set of positive integers into itself by this rule. F of n is n itself if n is even and n plus 1 divided by 2 if n is odd. Is f injective? Is f surjective? So here we are we have not been told that prove that it's injective or anything like that. It's more open. We have to figure out if it is injective, then we have to show it's injective. If not, that also we have to prove by some counter example. So here in the beginning itself we need that guesswork where we put some values of f and then try to figure out what it's really going to be. And there is a third part also. For each positive integer k, what integers does this set f inverse of k consist of? I seem to be running out of ink. Just give me a moment. So here we have to see some values in the beginning itself. Then only we can start the solution. Because we don't really know whether this function is injective and or surjective. So let's just put some values and try to guess. N f of n. 1, 2, 3, 4, 5, 6, 7, say. Alright, so what is the rule? The rule is that if our input is even, then the output is the input itself. So that immediately tells us that the output when the input is 2, 4 gives us 4, 6 gives us 6 and so on. But if the input is even, we have to add 1 to it and then divide by 2. 1 plus 1 is 2, 2 divided by 2 is 1. 3 plus 1 is 4, 4 divided by 2 is 2. 5 plus 1 is 6, 6 divided by 2 is 3. 7 plus 1 is 8, 8 divided by 2 is 4. And of course, other values also exist. Alright, one thing we can immediately see is that the function is not injective because this two distinct inputs 2 and 3 have the same output 2. So instead of simply thinking about what will happen here and there in air, just by looking at some values, you have already obtained an answer to this. F is not injective. So let's start the solution like that. Note that f of 2, because 2 is even, so the output is also 2. But 2 at the same time is 3 plus 1 divided by 2 and 3 is odd. So this is f of 3. Hence, f is not injective. What about surjectivity? For surjectivity, we need all the positive integers to appear here. Just by looking at these, we don't quite see that happening. Let's take some more values. Perhaps then we can see, it seems like it should be surjective, but let's see more values. After 7 we have say 8, 9, 10, 11, 12, 13. So 8 will simply be 8, 10 will be 10, 12 will be 12. 9 plus 1 is 10, 10 divided by 2 is 5. 11 plus 1 is 12, 12 divided by 2 is 6. 13 plus 1 is 14, that gives you 7. So we want all the positive integers to appear along the second row. 1 is appearing fine, 2 is actually appearing 2 times. In order to maintain a uniform pattern, we are not going to consider this 2. It is there, but instead we consider this 2. Why? This output 1 has come from an odd positive integer 1. This 2 also has come from the next odd integer 3. We also have 3, which comes from the next odd integer 5. Then 4 comes from 7, 5 comes from 9, 6 comes from 11. So this and 7 comes from 13. This gives us the guess that yes, it looks like f should be surjective. And it also tells us how to find the inverse image of an element. I should not perhaps say the inverse image, but an inverse image of any positive integer under f, because that's what we need to show that f is surjective, if really it is. Let k be any positive integer. Now, how can you guess the general thing? By going backwards. How do you get, it's somewhat difficult to figure out how you get 1 from 1. But how do you get back 3 from 2? Not by adding, but by following the opposite order of the operations. What did we do to 3 in order to get 2? We added 1 and then divided by 2. So multiply this by 2 and subtract 1. 2 times 2 is 4, 4 minus 1 is 3. 3 times 2 is 6, 6 minus 1 is 5. 4 times 2 is 8, 8 minus 1 is 7. Two times k is 2k minus 1 is 2k minus 1. Will that be our input so that the output is k? But do not forget that your input should lie in z plus, because z plus is the domain as well. If k is a positive integer, is 2k minus 1 also positive? Yes. K is positive means k is greater than or equal to 1. So multiplying both sides by 2, you get 2k greater than or equal to 2. Subtracting 1 gives you this. So yes, that is also a positive integer. Such that f of 2k minus 1 is equal to. But now which part of the definition of f will you use? The second part. Why? Because not only is 2k minus 1 positive, but just from the form of it, we can clearly see that it's odd. And that is why the output is this. If you do the calculation, you get k back. So, f is surjective. But that's not all. We have this third part also. For each k, we have to figure out precisely what this inverse image is. It's a set after all. We at least know that f inverse of k has this element, but it may have other elements also. No? For example, f inverse of 2 has the element 3 in it, but it also has the element 2 in it. So, what to do? How to figure out this set? And that's why I considered so many values. You may notice one thing, that some of these outputs are appearing only once, whereas some others are appearing twice. Not more than twice, but twice. 1 appears only once. 2 appears 2 times. 3 appears only once. 4 appears 2 times. Somewhat further apart than these 2 twos, but that's okay. We are not concerned about how far they appear from each other. After that, 5. 5 appears only once. You see, these are only guesses because after that also we have values. How do we know that another 2 will not appear? That's only a guess. We will have to prove this guess. Okay, so after 4, we have 5. It appears that 5 will appear only here and nowhere else. What about 6? 6 has appeared here and also here, again 2 times. Now, which ones are appearing once and which ones are appearing 2 times? You can see that the odd numbers are appearing only once, whereas the even outputs are appearing 2 times. Okay, so let's now next claim this. We next claim that for any positive integer k, f inverse of k consists of 2k minus 1 only. Never forget that an inverse image of even a single element is after all a set. It may have one element, but it's a set. By definition, it's a set. If k is odd and 2k minus 1 comma k if k is even. This is our guess. Okay. Note that in both the cases we do have 2k minus 1, which actually we have proved also. We already have 2k minus 1 in f inverse of k, regardless of the parity of k, whether k is even or odd, this is always the case. Now we have to consider 2 cases. Let k be odd. Okay. Now, is there something else, some other input other than 2k minus 1 that will also give us the output k? Let n be a positive integer such that f of n is equal to k. Our aim now is to prove that this n has to be equal to 2k minus 1. Okay. Suppose n is, see, being a positive integer, n itself is either even or odd. Suppose n is even, then by the definition of f of n is n itself, but then n becomes k itself. Is that possible? No, because n is even whereas k is odd. That's not possible. That means n has to be odd. But then f of n is not n, it is instead n plus 1 divided by 2. And if you now solve for n in terms of k, you get n equal to 2k minus 1. Hence, f inverse of k really is this singleton set 2k minus 1. We have actually proved. So this is one case where k is odd. Next, let k be even. Okay. Note that k, you see, k after all itself is a positive integer. No, I mean that's how we started. It's not here, but for every positive integer k, this was our claim. So k is positive and k is even means what? That f of k is also equal to k. F of 2k minus 1 is k, that thing is there. But additionally, because k is now even, f of k is also equal to k. Hence, k also belongs to f inverse of k. Besides having 2k minus 1, f inverse of k now has k as well. Is that enough? No. What if there is some other input also? Let n be a positive integer such that f of n is equal to k. All right. If now being a positive integer, see, our aim now is to show, just like that one, this case, now our aim is to show that either n is k or 2k minus 1. Now n being a positive integer is either even or odd. If n is even, then n itself is f of n, and that is equal to k. So in that case n is k. But if n is odd, then then f of n is n plus 1 divided by 2, but which is k, which implies same thing, that n is 2k minus 1. So in this case, this is really this pair set consisting of 2k minus 1 and k. This is where the solution in fact ends. But note that we could have done this third part alone, and from that itself we would have been able to conclude that our f is surjective but not injective. Surjective because the inverse image of any element in the second set is non-empty, and not injective because sometimes we have two inverse images. Okay, so if you simply do this third part, from that you can conclude the first two parts. But anyway, we did all the things. And finally, let's see the next one also. Let x and y be disjoint sets. So there is no element common between x and y. Suppose that f from x into y and g from y into x are injective functions. Injections are one-to-one functions. Define another function h from x union y into x union y by this rule. H of x is f of x if x belongs to x, and g of x if x belongs to y. Okay, so two sets are given which are disjoint, and there is a function f from x to y and another one from g from y to x, both of which are injective functions, and using them we have defined another function h from their union to itself, like this. Prove that h is also injective. Here also, to show that h is injective, we will take two distinct inputs and prove that the outputs of those inputs under h are also distinct. Okay. Let us remember that f maps x into y and g maps y into x. This one is not difficult. I mean, here we do not want any guesswork or any rough work. We do not need those things. Let um, say x1 and x2 belong to, keep in mind we want to show that H is injective, so we would take two distinct elements in the domain of H, X union Y, and depending on where the elements really lie, here also we will see 4 cases such that they are distinct. If you want, you can make the solution visually more appealing by writing case 1, case 2. Those things you can do. I am not going to do that. Let us first assume that x1 and x2 both belong to X. Since F is injective, f of x1 is different from f of x2, and it makes sense to consider the f images of these elements because they belong to X, which is the domain of the function f. However, by definition, those are also the H images. That's why we can at once write H of x1 is equal to f of x1 and H of x2 is equal to f of x2. But injectivity of f and distinctness of x1 and x2 implies that these two are distinct, and that way the H images are also distinct. Next, let x1 and x2 both belong to Y. You can guess, I think, what we are going to write next. Whatever we did here with F, now we are going to do the similar thing with G. Since G is injective and these are now distinct elements in the domain of G, which is Y. So H of x1 this time is G of x1 by using this part of the definition. That, however, is different from G of x2 because G is injective and this is H of x2. Next, let x1 belong to X and x2 belong to Y. Then H of x1 is f of x1 and H of x2 is G of x2. Oh, and one more thing, because f maps capital X into Y, so this belongs to Y. And G maps Y into X, so this belongs to X. Let me see, X, F maps an element of X into an element of Y, and G maps an element of Y into an element of X. Yes. Since X and Y are disjoint, their intersection is empty, so there is no element common. In particular, these two cannot be the same element. you can clearly see that the remaining case where x1 is in y and x2 is in x is similar. Similarly, if x1 belongs to y and x2 belongs to x, then also their H images are different. Hence, H is injective. Okay, so that way we have the proof. If you find that the other way of showing that H is injective is easier than this one, that also you can say, I haven't seen that, where you assume that H of x1 is equal to H of x2 and then somehow prove that x1 is equal to x2. That also you can try if that one ultimately turns out to be easier. But this is also one of the ways of solving this. So that's just it for tonight. Our next upload is, tomorrow we do not have any upload. The next upload is this coming Friday, where we keep solving more calculus problems. So see you on Friday with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.